Yeah. Okay, I think it's time to start the next talk in this session. So it's about graph algorithms in the MPC model, and it's by Slobodan Mitrovic.
Thank you. First of all, it's my great pleasure to be here, and I would like to thank the organizers for running this event. I'm very happy about this event. I'm looking forward to the rest and meeting all of you. So today, as Mozen hinted a few times in his talk, this is like continuation of what he talked about in terms of massive parallel computation. And I'll be telling you about some graph algorithms, more specifically about some graph techniques in MPC. But first, here are my mandatory big data slides. When we think about data today, here are some concrete numbers. The data that companies handle, they're really huge. And the most recent one is about a number of parameters in GPT-4 model, and apparently it's more than 1 trillion. There's some speculation. There's no exact number on the web, but apparently it's like 1.73 trillion. Those numbers are just huge, right? And even if you look more at how much money was spent, how many resources were spent to manipulate this data, handle this data, there's lots of money, much more than what we are getting from NSF for our grants. And here is a slide that I like to show to even in class, which I teach on distributed algorithms. I saw this a few years ago, and it says that the world's biggest data center is bigger than world's biggest airplane factory. And I have to tell you that I was skeptical about this when I saw it the first time. So, I searched the web, and I got some numbers. These numbers are in terms of area, right, in square feet. And it turns out that if this is your metric of comparison, this is really the case. And for me, it really does change the way I think about computation. And I think it will be affecting more and more the future of computation, both on theoretical and on practical end. But these data centers, they're huge. They have many computing units. And people have developed different kind of frameworks to write the code. It's not difficult to use this framework. I've used MapReduce myself at Google. It's not that difficult. You write some code, and then somehow the system does the magic. But people have developed different frameworks, and this is how we got to massively parallel computation model. Like, we theoreticians like to have a model that we can play with, something fairly simple. We can play with our favorite problems. And the right way to think about MPC is just as a theoretical abstraction of tools for handling massive data. And again, these are the tools, right? Some examples of them. And again, as was mentioned in the previous talk, I'm not going into details, but this model was introduced we got to this model through several papers, originally starting with MapReduce, but now we have this MPC model. And let me remind you of the model. Some of you might not have been here during the last talk, or maybe caffeine still didn't kick in during this slide in the last talk. So let me just briefly remind you, the model itself, it's very simple. You have number of machines in this model, say capital T machines, computing units. They perform some computation in synchronous rounds. Every machine can talk to every other machine. We think like the communication topology on them is a click. And I'll be throughout this talk talking about a space per machine. You can essentially think of as that to be a RAM that machine has and can use for its local computation. And what typically we like is that the total space across all the machines is enough to fit the input size, but ideally not more. I want to mention here that there are some very interesting results which use more memory than the input size. But whenever we can get something that is not much more than the input size, that's kind of ideal scenario in that sense. There is this constraint that no machine can send too much data per one round, can send at most S bits, and can also receive at most S bits. And our goal, as it is typical with distributed and parallel systems, is to solve a problem of interest in as few rounds as possible. So this is the model. And I think it's very useful to try to place MPC in some comparison with respect to existing models. Like MPC is a fairly new model. It was introduced less than 2 decades ago. But there are other models like those that we've seen in the last talk, like local, PRAM, which has been studied for a very long time. And it does make sense to ask what is the relation between MPC and those other models. And in fact, it was one of the very first questions people asked when they came up with the MPC model. So here is how I would like to make this comparison. This is one way of comparing these two models. There are more ways. So I'm having this positive orthant. And on the x-axis, I will plot space. What do I mean by space? I mean the space that your computing unit has. And on the y-axis, I will plot something which I call information speed. Now, what do I mean by this? Think about a graph problem, and think about your input being a graph. And what I'm asking, what I mean by information speed is the time in your model that you need to send one bit of information from vertex U to vertex V. Okay, only a single bit information between two vertices. So this is what I mean by information speed. Okay, the centralized setting, when all data that you have is at one place, this bar is the range of centralized setting. I mean that you have at least space on your machine to store all the input, but potentially a lot more than that. But then if you want to write something from cell of vertex U to a cell of vertex V, I'm assuming you know identity of vertex U and V, you need constant time to do that, right? Okay, so all of us are familiar with this. Then here is local. Model which was defined in the previous talk. I will not define what is local, but in local, the memory is not a concern. We allow lots of memory in terms of communication between computing units and also locally. But then if you want to send one bit of information from vertex U to vertex V, you actually need time, which is their distance. So if your graph has large diameter, and so there are two vertices, then if you want to send information between them, it can potentially take lots of time. Now on the other extreme is PRAM, is parallel RAM, where you have many CPUs, many computing units. All of them have very limited memory. Okay? But then again, they have shared memory. So if you want to write something from cell that corresponds to vertex U, from that cell to a cell that corresponds to vertex V, you also do that in constant many rounds. Okay. And here comes MPC. So MPC, this bar is the range that corresponds to MPC. So first, if I want to exchange a bit of information between two vertices only, U and V, you can do that in constant many rounds. It's like easy, really easy primitive. And when we think about space, when we think about space per machine, then somehow interesting regimes are when we cannot store all the input data. So it's slightly less than n. But also, we typically consider regimes of MPC where the memory per machine is polynomial in n. So maybe it's n to the 0.01. You can replace the 0.01 by any positive constant. And in some sense, if you ignore the number of CPUs or the number of machines that you would like to use in PRAM and MPC, MPC feels like stronger model than PRAM. And it was indeed one of the questions that people asked early on. I think paper in 2011, which talked about sorting in MPC and search. They even asked this question very concretely and tried to understand how you can actually shift algorithms, how you can take algorithms from PRAM and then move them to MPC, potentially and ideally with some speed up in terms of round complexity. And in a moment, I will get to a technique I want to talk about, which is also kind of inspired by this view. So this would be, again, placing MPC compared to a few related models. I want to say that there has been lots of connection between MPC and other models in terms of techniques. So in particular, many algorithms in MPC, they do build or borrow techniques from other models, but also it goes both ways. We have seen several times that an idea developed for MPC actually lifted back to another model, and then also give improvements for this other model. But today, I will focus on a single technique, on a very specific problem. The technique itself is simple, but I want to show you instantiation of this technique on a specific problem. And I was advised, or actually politely and friendly suggested by the organizers, to make the rest of this boring for the experts. Rest assured, I'm going to nail that part. But for non-experts, let's see how it goes. Very high level of technique that I want to dive into. And we call that technique simulation year-round compression. But here is the idea. There is a graph, and you want to solve some problem, say to find approximate matching. That's the problem we'll be looking at. And there is some algorithm A, which runs in T rounds. And maybe that algorithm is designed for the local model or for PRAM. So this is the algorithm you're starting with. And then you're simply asking, can I take this algorithm A and simulate in MPC, right? Somehow partition my graph, maybe do this multiple times, simulate in MPC, and get much fewer rounds. But now in MPC, the algorithm I'm going to use is A, or maybe some close variant to A. Okay, I'm intentionally using this like approximation next to A just to signify that the algorithm will end. Using an MPC is not necessarily the same as the starting algorithm, but it does resemble. And remarkably, this might sound like a very simple recipe, and it is, but there are a large fraction of results actually came out of doing this. Now, it does not mean that it's trivial to tweak this A, and it does not mean that it's trivial to get significant improvement in round complexity. That's where the main effort goes. But if you are thinking of your favorite problem, my friendly suggestion would be to actually also consider this if you want to, implement your problem in MPC. Just to think, can you somehow, especially if it's like for PRAM, can you somehow use this extra space on every machine to solve the problem of fewer rounds? And the specific problem we'll be focusing on will be approximating maximum matchings. In MPC, in this regime where every machine has a linear in the number of vertices space. Okay. Good. So the problem, to be more concrete, I want really to emphasize that we really do care about constant factor approximation, as there was also mentioned in the last talk. Sometimes properties like maximality can be more challenging, right, to achieve. What we're really happy is just any constant factor approximation. So, for instance, in this example here, if my algorithm outputs these 3 red edges, we are totally happy with this. Note that this edge down left, it can be also included in matching and make this output even maximal then, but we are totally fine with only these 3 edges. Okay, so this is what we want to solve. And when we talk about MPC algorithms, I promise you there will be one problem and one technique, but there are several components to this technique. And when we think about designing MPC algorithms, there are at least 2 things we have to decide how to do. The first one is how do you partition your graph, right? There are many ways to partition your graph, and it does affect the information that you will have on machine locally, and how then you will leverage that information by the algorithm you want to design. And the second part, and these 2 parts go hand in hand, is what is the algorithm that you want to run locally on every machine. So I will talk about each of the 2 parts separately, and then only at the end in our analysis, they will kind of come together. First is about graph partitioning, and what I will show you briefly and what we will use is random vertex partitioning. It was used in several papers. Mainly this first 4 are for matchings. This also type of partitioning was used for some kind of graph clustering, also gave improvement. And the very last result is for approximate triangle counting, and it kind of adds to the talk that we saw yesterday by Sash, where this kind of partitioning enables one to get somewhat better estimators. So, what is the partitioning itself? It's quite simple. We have a graph here, and in this case, in this example, let's assume we have 3 machines. These are 3 machines in our model, in our MPC model, and I will use delta to denote maximum degree in the graph, and I want to use root delta many machines to partition this graph. And I also want to think about each of these machines have a color, like all these machines say have colors between 1 and root delta. And then how is my partitioning working? Well, first, each of the vertices I will color with the color 1 through delta, uniformly at random and independently of other vertices. So this is the first step. And then on red machine, I will gather vertices which have red color on blue machine vertices which have blue color, and green machine vertices which have green color. And on each of those machines, I will look at induced graph. Okay, so this is how partitioning look like in this example. Notice that there are some edges, say with endpoints that have different colors, which do not appear here. They are somewhere in the system. We did not forget about them entirely, but in this partitioning, they just do not appear here. And as you'll see, it's not that important. We can still do a lot, even though we are ignoring many edges. Now, why are we using root delta many colors? Well, it is because it gives us that even with high probability, number of edges per machine is going to fit in our memory. So if you do some simple calculation, right? If you ask what is the expected number of edges on machine I, well, from linearity of expectation, I can write this, just as a sum across all edges, the probability that edge E is on machine I. But now there are at most n times delta edges, and the probability that an edge E is on a specific machine is the probability that both of its endpoints land on this machine, which is 1 over root delta squared, which gives us n. So the parameters are set in such a way so that you kind of get the most out of your memory if you use this kind of partitioning. And so that's it about the partitioning itself. Any questions so far? Okay. Now we come to the algorithm. What kind of local algorithm we want to run on every machine? I want to start with this algorithm which Moz in his talk described, which is this primal dual algorithm for finding a fractional matching, some constant factor approximation. And I will run through an example of this. So this is the algorithm I want to start with, my algorithm A that we had a few slides ago. Then we'll see how to change this algorithm to get some even nicer properties. So let me remind you of the algorithm. XC in this algorithm is just fractional matching on edge E. And originally, we start with XC is equal to 1 over n for every single edge. Every edge will have like a label, or will have a label frozen or unfrozen. Originally, every edge is unfrozen. And then we do the following. Until while there is some edge which is unfrozen, for every vertex V, we will look at what is the sum of the matching weight of the edges incident to this vertex V. If it's at least 1, we will freeze all the edges incident to this vertex V. Then after that, in step B, for each unfrozen edge, we will double the matching weight. So for instance, this bar here, say, is the value of YV in iteration 1. Originally, every edge has fractional weight 1 over n. Then say that no edge is frozen. We go to the next iteration. We double the matching weight of unfrozen edges. Then maybe these nodes A and C actually hit this threshold. So what we do, we will freeze the edges VC and VA, meaning that from that point on, their matching weight will not increase. It will stay as it is. So then we proceed. YV goes bigger. We go one more step, and then eventually YV, it becomes at least 1. Then we would freeze all the edges incident to V, And at this point, after this point, no edge weight incident to no edge, no fractional matching of edge incident to V is going to change. And we do that until there is some unfrozen edge. And at the end, we output x over 2 as our fractional matching. It's easy to convince yourself that this is really a valid fractional matching. And moreover, there are few simple properties. The first one is about the approximation. As it was already discussed, I'm doing here example for epsilon is equal to 1 compared to the previous talk. So this would give you 4 approximations. X is a vector. Yes. Thanks. Yeah. So we are. The question was, what is this x? X is just a vector indexed by the edges, and so we are outputting this vector, and every entry is divided by 2. So this algorithm gives you 4 approximation. Okay, it's constant factor approximation. How about the number of the loops, the number of iterations that this loop takes? Well, it's log n. Why? It's also fairly simple to see this. We start with edge matching being 1 over n, and each unfrozen edge in each iteration would double its matching value. But then no edge will go above 1. So you get log n iterations at most from this. There is the last property, which is actually quite important, and I will get to that as well. That assume that I only tell you at what iteration each vertex crosses a threshold. So instead of giving you x, I actually give you this information. When it happened that yv crossed this threshold. From this information, you can infer the entire x. Right? How, if you look at edge, say VE, if we cross the threshold in iteration 4, this crossed threshold in iteration 2, I know that the weight of the matching value of this edge should be 4 over n, right? Just due to the whatever was the minimum iteration when this threshold was crossed. So something to keep in mind. And this is all nice. And moreover, it's fairly easy to implement this algorithm in log n rounds in local in MPC. But let's go crazy with this. And I'm asking, let's try to even think whether we can implement this in all fun MPC rounds. I know the experts will tell, no, you need more. That's true, but let's just think about this, okay? And then we'll see what goes wrong, okay? Still, we'll be able to get much faster than log n. Okay. So here is an idea of how to execute this algorithm in MPC. And as a reminder, we are using this random vertex partitioning, meaning that we are randomly partitioning the vertices, looking at induced graphs, and then we want to run some algorithm. But how about on every machine, we actually run this algorithm? It's a valid algorithm, right? So we just run on every machine, but now instead of computing yv, which we cannot compute exactly because we are seeing only a sample of graph, we will use that sample to estimate yv. Okay, I will refer to this estimate as y tilde v. And then from this estimate, we will decide when to freeze the edges, right? Again, we only need to actually know when we cross this threshold. Right? So let's do that. Okay. So very simple idea. So let's see what can go wrong, and there is something that goes wrong. So this is YV, which means the value YV in the process, which is the full graph, and Y tilde V is the estimate of YV based on the sample that you have locally. Okay, so in iteration 1, both YV and Y tilde V say that they're below 1. They still didn't cross this threshold. It's all good, like behavior with respect to Y in the sample and the centralized algorithm is the same. Maybe you do iteration 2, it gets closer to threshold, still kind of on the same side of the threshold. That's good. You do one more, and then maybe this happens. Okay, that YV cross the threshold by tiny bit, but Y tilde V, it stayed below the threshold. Okay, after just very few iterations, this can happen. This can happen even in the very first iteration. But here is my question, if there is a volunteer in the audience. In the worst case, in the worst possible scenario, what is the probability that this happens? Because you can as well say, well, yes, this is a legit scenario, but how likely is this to happen? This happen extremely rarely. Okay, maybe we can handle this, right? But what does anyone want to guess, or just intuition? I hope my intuition is right about the number that you'll see in a moment. But does anyone want to guess?
No. Sorry, I think I missed how you are estimating. Like, how do you get Y tilde of A?
Okay, well, thanks a lot. So the question was, how do we actually compute Y tilde of V? On my sample that I have locally, I will sum up the x's and say times the number of machines, the number of colors I'm using. So in this case, times root delta. So this would be my estimate of YV. So I'm just again summing up what I see locally, but because I know that I'm seeing only 1 over root delta fraction of my neighbors, I will upscale this by root delta, so to get estimate of to get the estimate. Make sense? Okay, thanks. Okay, I think it's 1/2, and here is why. Just to give you intuition. Take the example when YV is exactly 1, and assume that you're having the local sample that you're using to estimate YV is amazing. In a sense, it's fresh randomness, it's independent randomness, right? And then when you use V tilde to estimate YV, tilde Y will be either slightly above 1. Again, I'm thinking of YV being 1, or will be slightly below 1. And this will essentially happen with the same probability, right? It will just be very tightly concentrated around 1, but maybe tiny bit below or tiny bit above. But this is fairly bad, because what it says, remember, we want to essentially execute log n iterations of this process. But what this intuition tells us is that it might happen for some vertices that even after few iterations, like 1 or 2, we actually get into this situation, that what our simulation in MPC is doing and what the algorithm on the full graph would be doing is with probability 1/2. It's with probability 1/2 off for even single vertex. And then I imagine this error accumulates very fast when you take more and more steps. So how do we fix this? Any guess for people who hasn't seen this? Yes. Please, thank you, Eric.
Maybe instead of saying either you completely freeze an edge or you update it, maybe you slow it down the way that you increase it.
That would, you mean to change these two to something which is smaller, or?
Right, I'm just saying that you want to transfer that there's going to be some error in the estimation, but the decision that you end up making is very discrete.
I see. Okay. That's quite nice idea. Even if what you're saying relate to paper which was before this, I can see resemblance. So yeah, I mean that feels something that could potentially work. Not what I will show, but so the suggestion was, instead of doing this freezing discretely, let's maybe do it continuously. It's not what I will show you, but I think it makes lots of sense. Okay, so let me show what I'm having in what actually the paper does. So the problem is that even if these, think about YV and Y tilde V being extremely close to each other, right? Just like, what Chernow bound gives you, like this close. It's very tightly concentrated. But the problem is that this threshold is there, and you can cook up examples where this bad thing happens. So let's do this. Let's just keep shifting our threshold. Just choose it randomly from a small range, and then see how it helps. Before I say how it helps, just as a brief comment, even if you write like this centralized algorithm, it's still constant factor approximation. It's really not hard to convince yourself that it's maybe, say, 5 approximation as opposed to 4 approximation. So in terms of approximation, there is no concern with the fact that you keep choosing random threshold. Okay? So I will not even go into that, but let's run what we have seen before on an example, just to make sure that we are on the same page with respect to this random thresholding. Okay? So again, our estimate Y tilde, now instead of 1, we are choosing some random number from this range. Okay. Again, this thing change. We run one more iteration, like some edges double their weight. So now we are choosing the new threshold. Notice that I'm again choosing the new threshold, although I'm thinking about the 2 same vertices, right? So literally every time I want to test this, threshold is new. Okay, so we do this, and then we do this. Once YV and Y tilde V, once both of them, if it happens that both of them cross the threshold at the exactly same time, even if they're not the same, these values YV and Y tilde V, this is the event that we really like. Right? This is something we are really happy with, because it gives us that timestamp. It gives us that timestamp when this event happened, which then we can use to actually infer what is the vector of x. This is the algorithm. Any question before I attempt to briefly analyze this? So I showed you this slide some time ago, and this would be, in that context, this would be algorithm A, but this one on the right side would be like this approximate version of algorithm A. Okay, it's not much different, right? I mean, this estimate part is I think is very natural, right? If you're running this on your sample, I mean, the best you can do is to somehow estimate, right? But so pretty much the main difference is replacing this like deterministic value, this like fixed, this constant, by something which is chosen randomly. But how much does it bias? How much if this is running in log n rounds, how many in how many rounds we can execute this algorithm, right? So this is now the question, and I will try to give a very brief analysis of this. To really show you the main idea, I want to simplify the setup just a tiny bit. I will think that delta is the maximum degree is n, okay, and then I will just have root n colors or root n machines that I'm using for my random vertex partitioning. And just as a reminder, what we really like when it happens is that when YV and the estimate of YV cross the threshold at the same time. We at least would like for this to happen with very high probability. Okay. And now I want to do some analysis, and I want to consider the case. I want to consider the perspective from a vertex which has fairly high degree. So this vertex has degree at least n to the 0.9. Let us look only at the very first iteration. Okay, just at the very first iteration of what we can say about how close YV and Y tilde V are. Okay, YV, it's very simple. It's just degree of V divided by n. Y divided by n because every edge is initialized to have fractional matching 1 over n. Okay, this part is easy. Now here is the estimate, and this is exactly what I answered to Sepper. But so how do you compute this estimate? Well, this term here under summation is just the sum of x's of the edges which are incident to V that you see locally. Okay, and then because you have root n machines, right? All the neighbors of V are uniformly partitioned across root n machines. I'm multiplying this by root n. I can additionally simplify this. Why? Because I'm talking about the very first iteration. And in that iteration, every single xc is 1 over n. So I will just pull 1 over n in front. So then this will become 1 divided by root n. But then, this is just the cardinality of this set. Simply the number of neighbors that V sees on the machine where it landed. Okay. Well, the expectation, it's right easy to compute. It's degree of V divided by the number of machines. And important part is that this is fairly large. You're probably guessing where I'm going with this. This is fairly large. This is n to the 0.4. Okay. Again, because I'm looking at the vertex which already has large degree to begin with. So I'm expecting to see lots of neighbors on its machine. Now, if you use Chernow bound, you have that with super high probability that if you look at actually the number of neighbors of V on its machine and the expectation, the difference is going to be like n at most n to the 0.3. It's going to be by n to the 0.1 factor less than the expectation itself. Okay, what does it tell us about YV difference between YV and Y tilde V? Well, I just have to kind of go back and plug in it here. So if you do it, it tells you that with high probability in the very first iteration, I'm now talking only about iteration 1, difference between YV and the estimate of YV is n to the minus 0.2. So it's tiny. Why is this helpful? Before we had this comment. And again, you can cook up an example where this holds even for iteration 1. Okay. How about now when we have a random threshold? I'm asking only about iteration 1. Only about iteration 1. Does anyone want to tell me, any volunteer, what do you expect then the probability to be that, you know, like this threshold, random threshold, cuts between, yes?
Roughly the difference between YV and YV.
Thank you, thanks a lot. It's exactly, it's this thing, or roughly that much, right? This 1.1 minus 0.9, this is just the interval range, right? From which for which we are choosing random threshold, and this is the probability. Well, if you compare 1/2 and this seems a lot smaller, right? Something that you can hopefully work with. If you want to think a bit differently about this, it tells you that if you now look at vertex W, it tells you that only tiny fraction of its neighbors will have some disagreement with this process, which is the full graph. But most of its neighbors will actually be following this centralized algorithm like this process, which is the full graph. Okay, we are almost done. I'm showing you thing about iteration 1. So I just want to give you, to share a few words about how this propagates, okay? And what we can expect to get this. But this is some nice progress compared to before, because again, the probability that things will go bad in the first round, in the first iteration, is almost negligible. Okay, so I'm still focusing on vertex, which has degree at least n to the 0.9. And we just did analysis and said that this is the probability that, you know, the threshold will cut between YV and Y tilde V. It's at most this much. And you can think about this probability as something is a thing coming from simply random partitioning. There is nothing else to what we have done than just doing random partitioning and then applying general bound, okay? And it's something that we cannot probably escape as long as we are doing random partitioning. But how about iteration 2, right? And here is what roughly happens in iteration 2. If you look at the neighborhood of vertex V, then for every vertex, either the green ones, either they followed either the YA and Y tilde of A were like in the same, following the same thing in centralized algorithm and in simulation. Say it happens for A, B, and C, or for some neighbors of Y or some neighbors of V, it actually happened that in iteration 1, this random threshold did actually cut between YV and the estimate of YV. You can think of this neighbor as, in a sense, polluting the estimate of YV, right? But the nice thing is that the fraction of this kind of neighbors, D and E, is tiny. Like, it's very small. And in fact, you can show then that if you now ask in iteration 2, what is the probability that the random threshold cuts between YV and Y tilde V, it is order of the error that we made in iteration 1, plus this term n to the minus 0.2, which is coming divided by 0.2, which is coming from random partitioning. Right? Even for neighbors, which were all totally fine, I still have this kind of random partitioning that happens right in the beginning, which does affect this estimate. But the point is that even in the second iteration, I'm not doing, again, full computation. You can show that this is at most some constant times sigma 1. And more generally, if you can formalize this, but if you keep doing this thing, you can show that after I iterations, the probability that the centralized algorithm and MPC simulation with respect to V are not in sync is, say, 10 to the I times sigma 1, at most that much. Now, we are happy as long as we have something like 10 to the I times sigma 1 is some super tiny constant. It just tells us that there is some very small fraction of vertices in the full graph for which things are not in sync. Right? And so we are okay with this. Now, this means that by what we have described, you can execute maybe log n over 1 million many iterations of that until loop. Okay, constant fraction of informations of iterations that loop has. And after that point, the probability of error potentially becomes too high. So what do you do then? Well, when that happens, you just resample everything, right? You get, once your probability of error becomes too high, you resample everything, and then you start simulating things again. Because once you resample, you get fresh randomness. Then again, you are in this regime of iteration 1, when you know that all your error is coming only from random partitioning, right? And then it accumulates bit by bit. The way I'm presenting this, and the way I'm talking about this feels like, yes, you do this like 1 million times, and you get to execute the full algorithm A, and it feels like it's constant. It has constant round complexity. I'm hiding some details here. The thing is that it's really that you can simulate only a constant fraction with this approach of your while loop. And it comes from the fact that, you see, I'm talking only here about very high degree vertices, but you need to handle also lower degree vertices somehow. But again, I will leave that maybe for after for a lunch talk or for this afternoon. But this is roughly the idea. Questions? Okay, so we are actually done with the algorithm and with this brief analysis. And what we have seen, the first thing was this random vertex partitioning. There is a bit of history behind that. Originally, some of these papers that Mosen in the previous talk discussed in the superlinear regime, they actually used edge partitioning. So it was originally unclear how to actually leverage random vertex partitioning and what it gives you. But it seems that if we couple this random vertex partitioning with some modification, or in this case with this random thresholding, at the end we actually go from log n MPC round complexity to log n rounds. And the best is not only constant factor approximation. There is even an algorithm that runs in these many rounds by Sohail and colleagues, which outputs even a maximal matching. The approach that I've shown you does not output maximal matching. You can round this and then boost this to 1 plus epsilon approximate maximum matching, but that's how far you can go with this. And this is just a brief overview of results and of the complexity that in general we have for approximate maximum matchings. Right, if you have strongly superlinear memory regime, as you saw this algorithm that runs in constant many rounds, we have like log n once we go to this memory regime, and then the best when you go below n is actually square root log n times log n around complexity. And I think I have a few more minutes, 2-3 minutes. Okay, thank you. Inspired by the SARS talk yesterday, I was like, I'm a bit jealous. I want to show if I can, some practical things as well. And I managed to find one plot related to this from my papers. Not much, but still, I will take it, and I can brag a bit. This is a plot from our work with Mosen and civil latency. This is related to computing clustering on graphs, but the point is that you might ask how efficient these ideas in practice are, and this plot was obtained by running things on Google system. Not even all the details that I know myself, but was obtained and running on Google system. And the difference which was used with this baseline, which is the blue line, the lower the better, by the way, it means faster. The difference is that this red dashed line corresponds to using random vertex partitioning. There's not that many things injected into the algorithm, but random vertex partitioning, from my understanding, is the main one, and it is much faster than what say they used before. And somehow I believe that Google wants to optimize their things, so it's supposed to be done on real data and on real benchmarks. So just to say that yes, in practice this thing can happen, and intuition is that random vertex partitioning kind of ignores lots of edges. And it does help when you're moving data around. Okay. So one slide on practical things, and well, I think I'm also out of time. And here are some open questions, which I think are quite interesting as a follow-up to this discussion. There is more to say about every problem. Like for set cover, those PRAM or local algorithms would give you a log square around complexity. Even this near linear memory regime, it's not hard to use these ideas that you've seen to bring this down to log n round complexity. But actually, it's not known how to go below log n round complexity. I think it's really interesting question, and somehow the problem itself have somewhat different nature. Like, yeah, some problem of set cover can be phrased and as finding matchings, but then there is a bit more to it, and it's unclear how to round compress this thing. I think it's really interesting problem. Problem two about improving the round complexity. It's probably my favorite one. Improving the round complexity to better than square root log n in sublinear memory regime. I'm actually not even aware of only square root log n. Do you know? Does anyone know whether you can use tricks to get only square root log n without times log n? So it might be that even that it could be interesting. I don't know, just to get square root log n of square root log n without any extra term. I know log n is tiny, but in terms of techniques, it might be very interesting to get this. And then here are two questions about denser subgraph. There's another very interesting question. Mosen mentioned this one, which is I also like that one a lot. How to get similar results for matchings in 3-rank hypergraphs. Somehow, like these ideas break for certain concentration bounds to bring you to give you this kind of speed up. And by this, I would conclude. Thank you.
Any questions? Slobodan. Yes.
Yes, please.
Sorry, I think I'm still a bit confused about how you do the estimation. Like, how do you calculate YV? So initially, you have square root of n machines, and when you're saying you're subsampling, are you subsampling each node in each machine with some probability? And then your n local is just the edges that the sample. Like, is that right?
Yes. So let me say it loud again. The question was, how do we actually compute this YV tilde? So first, our partitioning is we have root n machines, and every vertex chooses one of the machines uniformly at random. And then on machine, you only gather induced subgraph. And how I want to estimate YV? Well, the probability that a specific neighbor landed on the same machine where YV is 1 divided by root n, right? So whatever is my local estimate, I better upscale this by root n, just to account for the fact that the probability of that one particular neighbor being on my machine is 1 divided by root n. And then, as you said, you're totally correct. This means that I'm summing x is over the sample that I see locally.
So you do a random sample of the machine initially. You sample one of the machine.
Oh, no. So this is happening on every single machine. Yeah, sorry for the confusion. The question was whether we are doing on only one of the machines. No, root n machines are doing all of them in parallel. Every single machine would execute this tilde, this approximate A on its sample locally, and all of them are doing that independently.
So n locally is just for one machine, or is it
for only a single machine?
One.
And in particular, thanks. Sorry for not emphasizing this. N local of V means what are the edges incident to V on the machine where V landed, only on that one specific V. Because we are doing vertex partitioning, V is going to land on one of the machines, and only single one. And N local refers to the edges incident to V on that machine.
And is there an intuitive reason why those edges that have two colors don't really matter?
Why we can ignore them? That's an excellent question. You can show the analysis, but for high degree vertices, the reason why you can ignore them for these vertices that have large degree is because it's enough for you to work with smaller sample. But in fact, we don't know how to, if you would take more edges, like not do vertex partitioning, but just take more edges in addition to your induced subgraph, we don't know how to actually leverage those things. There might be a way, but we don't know. Yeah. Previously, again, before this kind of partitioning, there was, to the best of my knowledge, we used edge partitioning. Somehow this random vertex partitioning ignores edges, but it gives you nice correlation between the edges that you gather. This is like the best intuition I have. When you sample edges, it really hits these very, 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 very dense parts of the graph. But this kind of gives you nicer range, this random vertex partitioning at the expense of ignoring some edges. It gives you nicer range in terms of degrees that you can handle.
Okay, let's move. Yes?
And then do we aggregate the results from all the machines, and does that improve the estimate?
Excellent. So there was a question, thank you. There was a question whether we aggregate results from all the machines, and the answer is yes, absolutely, because those edges that we ignored, they still have some fractional matching. But again, the nice thing is that if I manage to tell you when every vertex hits the threshold, if I give you that information, you can use that information to write down your fractional matching. And so once you get that information, you can go back to the edges that you have ignored as well and say, oh, look, this is your fractional matching, just following this fact. But yes, this is a great question and something that is used implicitly in the analysis. We eventually go back to it.
Any more questions? If not, then let's thank Slobodan again.
Thank you.
And we'll reconvene after lunch at 2.